Hi, I'm Jade. This is my first talk, and today I'd like to talk to you about the possibility of snowball bifurcations on tidally locked exoplanets, so orbiting M stars. Okay, so as everyone in the room here knows, by now we've found many exoplanets, and much of the field's focus is on trying to figure out which ones of those could be habitable. Now, to know that, we need to know which ones can support surface liquid water, because habitability is a surface property. Okay, now a major factor that can affect a planet's habitability is the ice albedo feedback. So here on the left, this very simple cartoon illustrates the effect. So we know that the ocean absorbs much more solar radiation than ice, which is very reflective. So if we were to increase the insolation on the planet, we would have melting of sea ice, which will decrease the albedo and induce more melting. But if we were to lower the insolation, we would have some sea ice forming, which will increase the albedo and induce more freezing. So because of this nonlinearity, a planet like the Earth can have two stable states for a range of insolations. So we can look here at the plot on the right. Here the vertical axis is the sign of the ice latitude. So the ice latitude is the latitudinal extent of ice on the planet. And the horizontal axis is the insolation. The solid lines represent stable states and the dashed line unstable states. So if we start at the top right with a planet like the Earth, like modern Earth in its warm state, and we decrease the insolation, eventually, it will jump into a snowball state right there. Now, to get out of this snowball state, we would need to increase the insolation, but much more than the glaciation insolation. So a planet might have a hard time to escape that snowball state, and this could have bad implications for habitability. But at the same time, although I'm not an expert on this, for Earth, like going through a snowball stage has been associated with a rise in oxygen and in complex life. So it could be a good thing, but still up for debate. So, okay, now on this beautiful figure, again by Sunny, we see that the boundaries of the habitable zone strongly depend on the stellar type. So for an M dwarf here, which is much smaller and dimmer than a G star, the habitable zone is much more close in. So in fact, it's so close in that a planet that's orbiting in the habitable zone of those M stars are close enough to likely become tidally locked, as we see here. So this means that one side of the planet will always be facing the star, and the other side will always be facing away. So because those planets orbit their stars in such a different manner than rapidly rotating planets like the Earth, we want to know whether they could still go through a snowball bifurcation, like we know the Earth can. Now, there's already been some work done on the subject. First, let's look here at those two plots by Joshi in 2012. The top panel shows that the peak of the stellar spectrum of an M star is at a higher wavelength than that of a G star. And because of this, the ice albedo of a planet orbiting those M stars will be much lower. So the nonlinearity of the ice albedo effect will be reduced, and we can imagine that a planet orbiting an M star might have a more difficult time going through a snowball bifurcation because of that. And also, more recently here, Shields in 2014 showed that for an M star compared to a G star, the range of insolation at which there is bistability is much smaller. So again, a planet might have a more difficult time going through a snowball bifurcation. Now, both of those works were about comparing the different stellar spectra of an M star and a G star and seeing how orbiting an M star might make it more difficult for the planet to go through the bifurcation. But what we want to know is whether or not the fact itself that the planet is tidally locked, whether it's orbiting an M star or a G star or whatever, could make it more difficult to go through the bifurcation. Okay, so we used a global climate model called PLASM, so it's a 3D GCM of medium complexity. We set it up in a modern Earth continental configuration, computed clouds, and kept the CO2 fix at 360 ppm. And here's what we see first for the Earth. So here the top panel is the surface temperature, the bottom's the sea ice cover, and again, the horizontal axis is always insolation. The red stars here correspond to a warm start, so where the planet is completely ice-free. And the blue stars correspond to a cold start, so where it's completely ice-covered, both of those initially. And we see that we retrieve the expected snowball bifurcation here, and we have bistability. So great, the GCM reproduces the very well-known result for the Earth. But now, using it in a tightly locked configuration, we see something quite different right here on the left. So whether we start cold or warm, the surface temperature increases or decreases linearly with the insolation. We don't see a snowball bifurcation. Now you might be wondering about this small gap right here in surface temperature for those intermediate ranges of insolations, but this is not real hysteresis. It's actually just a model artifact due to the simple CI scheme of the GCM we're using. I don't want to get more into it now, but if you'd like to know, you can always ask me later. But what's really important is just setting up the planet in the GCM in a tightly locked configuration gets rid of the snowball bifurcation. And this is with a G-star spectrum, all right? So we can imagine that if we had used an M-star spectrum, it would be even less likely to go through a bifurcation. Okay, now how can we understand this? Well, we can use a simple energy balance model right here where the absorbed solar radiation is equal to the outgoing long wave plus the heat transport, both parametrized. So first for the Earth, here's an example state for the planet. And what's important to note right here is, so this is the equator in the middle, it's that the insolation shape is flat around the equator, right? We don't see a super sharp increase in insolation from the pole to the equator. Now, solving this EBM for the ice latitude, so again, the ice latitude is the latitudinal extent of the ice on the planet, we retrieve the bifurcation diagram that I showed and explained at the beginning, so where the planet can jump into a snowball state here. Okay. Now, setting up the EBM in a tightly locked configuration, what's important is that the insolation increases really sharply from the terminator, which is here, to the substellar point, which is here, right, compared to the Earth, which was much more flat. Now, solving the EBM again for the ice latitude, the bifurcation diagram here shows no bifurcation. So it looks like the EBM is able to explain what's happening in our GCM. Now, I'll just note that we are able to retrieve the bifurcation in this tightly locked configuration in our EBM if we just greatly increase the heat transport. So let's just keep this in mind for the next slide. Okay, so this slide explains what's happening in the EBM. But before looking at it, ultimately what you need to know is that whether or not the planet goes through the bifurcation depends on the insolation shape. So let's first look at the right here for the case where the planet does go through the bifurcation. So we have the ice line somewhere between the pole and the equator, and we perturb it slightly towards the equator. Now there, the insolation and the heat transport will be greater. But because, as we saw for the Earth, the insolation shape is not so sharp around the equator, at that point, the heat transport will actually have increased more than the insolation increased. And because of this, the ice line will continue all the way to the equator. So the planet is in a snowball state. Now, on the left, for the stable case, for example, for a tightly locked planet, again, we have an ice line somewhere between the terminator and the substellar point, and we again perturb it slightly, so towards the substellar point this time. But because, as we saw, for a tightly locked planet, the rise in insolation is so sharp from the terminator to the substellar point, this time the insolation will have increased more than the heat transport. And because of this, the ice line will return to its original position. So the planet doesn't go through a snowball bifurcation. So this is my conclusion, that tightly locked exoplanets are unlikely to go through a snowball bifurcation because of the sharp increase in insolation from the terminator to the substellar point. And we have a paper in prep on this that will be submitted soon if you're interested. Thank you.
Hi, my name is Richard Archer from the University of Colorado Boulder. I thought that was a really great presentation, so congratulations. I have a question regarding volcanism. So in terms of snowball Earth, there are people that suggested that the release out of the snowball Earth condition was driven by volcanic CO2. So after snowball Earth, you actually have a very large greenhouse effect. And I just wonder what you think that might apply to your model.
So that's to get out of the snowball once you're already in it. Volcanoes could outgas a lot of CO2. right. I mean, we just saw that tightly locked planets don't go through the snowball bifurcation, but yes, they can be in a snowball state if you decrease the insolation enough. However, to get out of this snowball state, it would be much easier than for the Earth because it's not a bifurcation. So you would just need to slightly increase the CO2 or...
I kind of misphrased it. I actually was wondering if you think that it would be an aggravating factor leading your planet to maybe a much hotter climate than you would have.
Oh. So you mean, for example, if we had tried using the GCM with a much higher CO2 level?
Well, variance is, we can talk about it. I don't want to dominate.
Sure, okay.
Yeah, I was just wondering, the result here, the tidally locked exoplanets unlikely to go through a snowball, is that conditional on assuming that there is not any heat transport from the insulated side to the shadow side of a tidally locked planet?
No, there is heat transport.
So that you have a basic model of default, this is how much heat transport you have, and then you still get and you still get a, let's say you do not go through the bifurcation, but if you increase that above what you expect, then you do go through
the heat transport.
Yes.
Yes. Yeah, you're actually, yeah. Actually, it's interesting that in the GCM, I didn't present it in the talk, but we found that the heat transport on the tidally locked planet is much greater than for the Earth. And it's great enough that in the EBM we should be able to get the bifurcation back, but the difference in albedo is smaller than for the Earth because of so many clouds at the substellar point, and this still gets the tidally locked planet to not go through the bifurcation. So yes, heat transport is really important. It's definitely happening, and it's enough to normally go through a bifurcation if that albedo range wasn't smaller.
Thank you.
Any more questions? If not, we can give Jade a round of applause. Thank you very much.